would like to introduce the first speaker, Alberto Gonzalez from Lomartov. Alberto Gonzalez is a sustainability engineer. Lomartov is an enterprise, Spanish enterprise specialized in supporting R&D, industrial and technological projects. They are focusing on life cycle based sustainability assessment, eco-design and circular economy approaches. Alberto focusing on evaluating the electrochemical, economic and social implications of emerging technologies. And he has a strong expertise in electrochemistry, including batteries and hydrogen systems. Alberto works within European projects, contributing to the development application of LCA, LCC, social LCA, and safe and sustainable by design methodologies, eco guidelines, and decision support tools for technology developers. Alberto is currently working in Solve, and Lomartov is a partner of the Solve project. And within this framework, he's involved in the assessment of solid-state battery materials, components, processes, and his activity spans from early design stages to the final validation of the final prototypes. Today, he will give a lecture providing an overview of sustainability challenges in solid-state batteries. And he will present how the SOLVE project uses LCA, sustainability by design, and eco-design principles to guide the battery development. So with this, I will give the floor to you. You can share your screen.
Okay, thank you very much, Daniele, for the kind introduction. I will share my screen, one moment. Okay. Do you hear me right, and can you see the screen?
Yes.
Okay, perfect. So thank you very much to all of you for coming to this third day of the Solve Summer School. As Daniele mentioned, I wanted to today to showcase a little bit what we at Lomartov do at the Solve project with all the sustainability guidance and validation of the technology. So I decided to call this lecture from battery innovation to sustainable design, the Solve approach to solid-state batteries assessment. So this is a little bit the list of contents that I'm going to follow during the presentation. I'm going to provide some insights, generally speaking, on sustainability in batteries. We'll then delve into which are the main challenges in solid-state batteries and which is the approach adopted in Solve to address them. And finally, I will showcase a case study of one of the family of materials that we have assessed in the preliminary sustainability assessment to see how these tools and methodologies that we adopt can tackle these challenges. So first of all, I want to start talking about sustainability in general. Historically, the global perception has often been that a technology can be considered sustainable if its environmental impacts are low. However, this is just a part of the picture, and sustainability is a broader concept that relies on three complementary dimensions, which are the environmental, the economic, and the social one. First, the environmental dimension looks at how a technology affects the natural environment, and this includes aspects such as climate change, resource use, energy demand, water consumption, toxicity, waste generation, or circularity among the most important. In the case of batteries, this is especially relevant because the material extraction, the precursors production, and in general, the cell manufacturing and the end-of-life treatment can all generate significant environmental burdens. Then the economic dimension considers if the technology is economically viable and scalable. A battery technology may show excellent environmental performance, but obviously, if it is too expensive, relies on very complex processes, or cannot be produced at industrial scale, its real-world implementation will be quite limited. So this is why parameters such as cost efficiency, market viability, and value creation are also essential sustainability criteria. Finally, the social dimension focuses on people and society, and it includes aspects such as the worker safety, the supply chain ethics, the community impacts, or the responsible sourcing and social acceptance. This is quite relevant because many raw materials are linked to complex global supply chains, where mining, processing, and manufacturing conditions have direct social consequences. So to assess these three dimensions, there are different life cycle-based methodologies that are commonly used. In the first place, life cycle assessment evaluates the environmental impacts, life cycle costing evaluates the cost along the life cycle, and last, the social life cycle assessment evaluates social and socioeconomic impacts across the whole value chain. LCA is standardized mainly through ISO 14040 and 14044. Social LCA has its own ISO standard, which is the 14075, published in 2024. And in the case of life cycle costing, this is slightly different because there is no single universal ISO standard. Instead, the IEC 60333 from the International Electrotechnical Commission is often used as a broader reference for the life cycle costing calculation. Although they focus on different dimensions, these three methodologies share the same underlying logic, and it's that they analyze the technology across the full life cycle, from the raw material extraction and material production through the manufacturing and use phase, and finishing to the end of life management. This life cycle perspective is quite relevant because it helps us avoid shifting impacts from one stage to another, or from one sustainability dimension to another. So the key message here is that a sustainable battery is not just a battery with a low carbon footprint. It should also be economically feasible, socially responsible, safe, functional, and compatible with circularity principles. So now, talking about why sustainability matters in batteries, first, we must address a fundamental paradox regarding the energy transition, and it's that batteries are a clear driving force for decarbonization. This is obvious. They are essential for meeting the European Green Deal targets and enabling this transition to a low carbon economy, particularly through the electrification of transport. However, batteries are not exempt from environmental impacts, and while they drastically reduce the emissions and impacts during the use phase by replacing these internal combustion engines, we observe that a significant shift of the environmental burden goes upstream. So this means that the most intense environmental pressures, such can be the greenhouse gas emissions and the resource depletion, are now concentrated in the raw material extraction and manufacturing phases. Then we also have some key sustainability bottlenecks or challenges that we must overcome regarding especially lithium-ion batteries, and are the following four. In the first place, we have the material scarcity and criticality. This is because we rely on a limited supply of minerals like lithium and cobalt, for example, and the rising demand has led to a price volatility and a dangerous dependency on geographically concentrated supply chains. For instance, since 2015, the prices of cobalt and lithium have increased by 3 and 4 times respectively since. So we have in the second place a high carbon footprint because the processing of materials and cell production remains extremely high energy intensive. So often, if we rely on energy mixes that are not yet fully carbonized, we are compromising the environmental performance of the battery. Then we are approaching also the performance limits. The current liquid electrolyte technologies are reaching their theoretical limits in terms of energy density. And if we want to continue increasing, especially the vehicle range without adding excessive weight and material volume, chemistry safety is required. Finally, and perhaps most importantly, the current industrial routes are largely linear, so we still face a major circularity gap where we produce, use and dispose of batteries without a robust system for the mass recovery of materials. These challenges define the sustainability gap that the next generation technologies must fill, and this is where solid-state batteries and the solve concept can intervene. By applying eco-design principles and safe and sustainable by design approaches, we aim that the next generation of batteries is not just high-performing, but also fully circular, and resource efficient from the very first day of design. After looking at these main sustainability challenges, it is important to understand that sustainability is no longer only a voluntary objective or a research recommendation, and particularly in Europe, it is increasingly becoming part of the regulatory framework for the battery development and market access. Here are summarized three of the most important regulatory drivers that are shaping the way batteries are designed, produced, and assessed in the European Union. In the first place, we have the EU Battery Regulation, which is the most directly relevant framework for battery technologies. It entered into force in 2023, and its scope covers all batteries placed on the EU market, introducing battery-specific requirements related to carbon footprint, recycling efficiency, performance and durability, and also recycled content. So for battery developers and manufacturers, this means that environmental and circularity-related data will become increasingly important throughout the whole design process. Second, we have the Eco-Design for Sustainable Product Regulation. This one has a broader scope because it applies to products in general and not just to batteries. And however, it is also very relevant for battery technology because it reinforces key eco-design principles such as the durability, the repair and maintenance, the recyclability, the energy and water efficiency, and the use of recycled materials. In practice, this pushes product developers to think about sustainability from the early design stages rather than treating it as something to be checked only at the end. The third one is the Critical Raw Materials Act. This regulation addresses one of the most strategic challenges for batteries that was presented before, that is the dependence on critical and strategic raw materials. This is because batteries rely on materials such as lithium, cobalt, nickel, manganese, graphite, and many others that have geographically concentrated supply chains. And this CRM Act aims to strengthen the European Union supply security by promoting domestic production, domestic processing, and also recycling, while also limiting the excessive dependency on a single third country. So the overall message is that sustainability requirements are moving from nice to have to must have, and battery technologies will increasingly need to demonstrate not just good electrochemical performance, but also lower its environmental impacts, a better circularity, and in general responsible material sourcing and a stronger supply chain resilience. After looking at the regulatory drivers, the next question is how we translate these requirements into actual design decisions. And here is where eco-design becomes relevant because eco-design means integrating environmental and circularity criteria from the early stages of product development, rather than assessing impacts once the product has already been defined and launched to the market, for example. In the case of batteries, this means that making design choices that reduce the material and energy use can extend lifetime, avoid or minimize hazardous substances, improve the efficiency, and in the end, facilitate the end-of-life recovery. For battery technologies, this is relevant because many sustainability impacts are locked in very early, such as the choice of active materials, the electrolyte chemistry, current collectors, coating, additives, etc., or simply the processing routes that can strongly influence the environmental impacts. And also another dimension such as the cost, the safety requirements, the criticality, and the recyclability. On the other hand, we also have the safe and sustainable by design approach that builds on this logic, but it takes a broader perspective. It combines three key ideas that are that the technology should be safe, meaning that risks for people and the environment are minimized. That is sustainable, meaning that environmental impacts and circularity are considered across the whole life cycle. And competitive, meaning that the solution must still deliver good technical performance and be economically viable. To combine these three ideas properly, it is necessary to have a life cycle thinking approach, reliable data, collaboration between the technical and the sustainability teams, and a continuous improvement and a series of iterations as the technology matures. So in summary, eco-design and safe and sustainable by design can help us move sustainability from a compliance requirement exclusively to a practical decision support approach for developing better battery technologies. So now we enter in the second part of the lecture, which are the main solid-state battery challenges and the approach adopted within Solve. And before discussing which are the main advantages and challenges of these kind of batteries in detail, it is useful to briefly look at which are the main application of the technology. As shown on the right, SSBs are being explored for several applications, but however, the most relevant for the presentation and in the end for the context of the Solve project are electric vehicles and aviation. In the former, the interest is clear. This is because the sector needs batteries with higher energy density, with improved safety, with longer lifetime and faster charging, but while keeping cost and environmental impacts under control. And if this battery can deliver high gravimetric and volumetric energy densities, they can help us increase the vehicle range or reduce the battery mass for the same autonomy. In the case of aviation, these requirements become even more critical because weight is one of the main constraints. So any improvement in specific energy can have a direct effect on the aircraft performance, on the payload, and in the end in the autonomy. At the same time, safety is absolutely essential because battery failure scenarios are especially sensitive in aviation applications. So now I'll focus on some of the potential advantages of solid-state batteries. It is important to note that this can vary a lot depending on the characteristics such as the final decided chemistry, the cell architecture, the manufacturing routes, the lifetime achieved, and the end-of-life strategies, among others. In this case, the main principle in this kind of batteries is that the liquid electrolyte is replaced with a solid one. And the first advantages this can bring is related to safety, because by reducing or avoiding flammable liquid electrolytes, SSBs can lower some of the risks associated with conventional lithium-ion batteries. However, this does not mean intrinsically that safety challenges disappear completely, especially when, for example, lithium metal is introduced in the concept. The second key advantage is the potential increase in energy density, as already mentioned. This is shown in the graph on the right side. While current LFP and NMC lithium-ion batteries already provide good performance, but we are approaching the theoretical limits, as mentioned before. And there are several SSB concepts, especially the ones with lithium metal and anode-free configurations, that theoretically can reach higher gravimetric energy densities. This is important for mobility because obviously higher values of watt-hour per kilogram can translate into either longer driving ranges or lower battery mass for the same energy capacity. This is directly linked to the third advantage, which are the lithium metal and anode-free concepts. And this is because by reducing or removing the conventional graphite anode, these architectures can reduce inactive mass and open the door to more compact cells with higher energy densities. There may also be gains in terms of lifetime and fast charging, but this is also highly dependent on interface stability and lithium plating control. And also from a sustainability point of view, one of the key expected advantages is a lower carbon footprint, with potential reductions between the range of 20 to 25% compared to current LFP and NMC technologies. With higher energy densities, the amount of active material, current collectors, structural components, which are required per kilowatt hour of delivered energy, can be reduced, as well as the potential simplification of the cell design and the manufacturing steps. Nevertheless, this reduction is not guaranteed and depends strongly on the financial architectures in material choices and in the end in the production processes. Logically, these come along with several potential challenges that also need to be addressed. The first one is the cost and scale up. Current LEAFs are already extremely competitive with pack prices that are close to $100 per kilowatt hour range. In the case of SSBs, the challenge is to manufacture thin solid electrolytes, lithium metal interfaces, and high loading cathodes at an industrial scale and also at a competitive cost. In the second place, we have the interface stability. In a liquid battery, the electrolyte can wet the electrode structure, but in the case of SSBs, the ion transport depends on the solid-to-solid contact, and if this contact is poor, the interfacial resistance and the degradation can limit the performance of the battery. Third, we have the dendrites and the lithium metal control. Lithium metal is one of the routes to higher energy density, But if the lithium plating is uneven, there are local current hotspots or defects in the electrolyte, it can still lead to short circuits or accelerate the degradation of the battery. Manufacturing complexity is also another major point. Solid-state batteries require very good control of layer thickness, pressure, effects, interfaces, and processing conditions. And this makes scale-up more challenging than simply replacing one material in a conventional battery line. Finally, material criticality and end of life also remain open questions, and SSB may reduce some impacts, but they can also introduce new materials, new coatings, solid electrolyte formulations, or fluorinated components that need to be addressed carefully. And also the recycling routes are also less mature than in the case of conventional lithium-ion batteries. So the question is, how does Solve address these sustainability challenges that I presented? Well, sustainability is integrated into every step of the project, from the materials we select in the lab to the manufacturing routes we choose, and right through how we plan for the battery's afterlife. We are moving away from traditional wet methods and exploring solvent-free dry extraction for both the hydrosolid polymer electrolyte and the cathode. And this is a massive step forward because it allows us to avoid toxic solvents like the case of NMP, and skip some energy-intensive drying steps. This approach could slash the processing costs by around 30 euros per kilowatt hour of delivered energy. Second, we are tackling material scarcity head-on through the two target concepts that you see on the right, the lithium metal and the anode-free anodes. By using this ultra-thin lithium metal, or even eliminating the excess lithium entirely with the anode-free designs, we can significantly reduce our lithium footprint. And at the same time, we are prioritizing low or no cobalt cathodes, which is vital for reducing both the environmental impact and the supply chain risks. Third, we are trying to break the old linear habit of batteries, the produce, use, and dispose model. In Solve, the design for this assembly is part of the design logic from day one, and this leads directly to our recycling targets. We aren't just aiming for the status quo, we are developing dedicated routes that aim to reach around 70% of a total recycling efficiency. And specifically, we aim to recover like 80% of the lithium and up to 95% of cobalt, nickel, and the copper employed in the cells. Finally, we are also designing for intrinsic safety by employing non-flammable hybrid solid polymer electrolytes and protective coatings on the cathode active materials. We are reducing the flammability risks from the inside out. When you add all of this up, our goal is to prove that high performance doesn't have to mean a heavy environmental burden, and we are targeting for example, expected cathode footprint values of 58 to 60 kilograms of CO2 equivalent per kilowatt hour, which should be around a 24 or 25% reduction compared to lithium-ion batteries that we employ today. Within the project, sustainability is addressed through two complementary phases. The first one is the early stage guidance, and the later as a final validation of the developed technologies. The first line represents the guidance phase. On the Lomartov side, task 1.4 focuses on eco-design guidelines. And here the idea is to assess material and component alternatives while the project is still at an early design stage, when decisions are still flexible. In parallel, task 1.5, led by Accurec, focuses on SSB design for recyclability, so that the end-of-life considerations can also be integrated from the beginning. The second line represents the validation phase. Later in the project, task 4.4 will assess the environmental and economic impacts of the financial technologies. And in parallel, task 3.5 will focus on the safe recycling of the developed solid-state battery components. I will not go into further detail on the recycling part because David from Accurec will cover this in depth in the next lecture. Then on the bottom of the slide, there's a figure that shows the transition from task 1.4 to task 4.4. In the first one, we assess each battery subcomponent separately. The adopted scope here is the cradle to gate one, so we can focus on the upstream impacts, the raw materials, the precursors, and the synthesis. And here the outcome is not a final product footprint, but eco-design recommendations and a sustainable and safe and sustainable by design material scorecard that will be shown later on during the lecture. Then in task 4.4, the perspective becomes broader. Here the assessment will move towards the integrated soft technologies. So the final prototypes are assessed with a cradle to grave scope. The functional unit will also change. Instead of assessing materials per mass or per theoretical capacity, we will assess the impacts per kilowatt hour of delivered energy by the solved cells. So now we enter into the last part of the presentation, and I'm going to show you a little bit about from Lomartov what we've done so far in Solve for the sustainability assessment part. So the assessment has been conducted at 2 different levels, employing 2 different methodologies, which are the streamline LCA and the development of a safe and sustainable by design materials scorecard. Starting with the streamline LCA, it follows the conventional approach of life cycle assessment, and it is normally structured around 4 main and different phases. The first one is the definition of the goal and scope. This is what we want to assess, where the boundaries of the system are, which is the functional unit we employ, and the latter is the unit on which all the calculations are performed, so different systems can be assessed in a fair way. This is also very important if we want to compare different kind of chemistries or with different baselines. Second, the mission is to build the different life cycle inventories, which means collecting all the inputs and outputs of the system. And this includes the use of raw materials, energy consumption, emissions, waste streams, and so on. Third, we perform the life cycle impact assessment, where these flows are translated into environmental impact categories. And finally, we interpreted the results, identifying the main environmental hotspots and areas of improvement. In our case, the scope was simplified to a cradle to gate approach, as mentioned before. And this means that we consider the upstream stages, the raw material extraction, the precursor production, and the material manufacturing. We did not include at this point the use phase and the end of life considerations, mainly because Solve was still in an early stage and reliable data available for financial performance, for use condition and recycling were not yet available. As you can see, there are different LCA boundary approaches. For early material screening, cradle to gate is one of the most practical options because it allows us to compare alternatives before the final technology is fully defined. Regarding the functional unit, most materials were assessed per 1 kilogram of synthesis materials. However, for the NMC powders on the cathode active materials, we used 1 million per hour of theoretical capacity. Whenever possible, life cycle inventories were retrieved from literature following a pragmatic approach. This was the first option because we wanted mainly in this first part of the assessment to focus on the impacts deriving from the different raw materials and how this could vary independently on where is this material produced, so it can be valuable and viable for every partner. And when these direct LCAs were not available, we modeled the different synthesis routes, employing information from scientific papers, patents, or experimental procedures. For the background processes, we employed the EcoInvent 3.11 database, and the impact calculations were performed in the CIMAPRO software. Another important point is that the comparison was always made within the same battery subcomponent category. And this, in other words, for instance, cathode coatings were compared with cathode coatings, lithium salts with lithium salts, and so on. And this is essential because materials have to be compared only when they are intended to provide a similar function or service. Finally, here are the impact categories which were considered in the initial assessment. The calculation method employed was the so-called environmental footprint 3.1, which is the one that is aligned with the requirements of the European Commission. The full method includes 16 impact categories, but since this is a streamlined assessment, at the beginning we selected 7 categories to keep the analysis focused and manageable. These categories are also commonly used in LCA studies of battery and SSB materials, and this is because they capture the most relevant environmental concerns, such as the climate change, the ecotoxicity, the human toxicity, both cancerous and non-cancerous effects, the resource use of fossils, of minerals and metals, and finally the water use. So here the idea is simple. Instead of trying to produce a full final footprint at a stage where many design parameters are still uncertain, we use a streamlined and comparative LCA to identify early hotspots and guide better material decisions while there is still design flexibility. To complement this streamlined LCA, a material scorecard based on the safe and sustainable by design principle was also developed with the project. So more sustainability dimensions are evaluated apart from just the environmental one. The starting point is a comparative screening of the material alternatives. In this case, we are not, as mentioned, assessing the final component, final complete battery cell, because the project is still at an early development stage. Instead, we compare materials within the same battery component family in the same way as in the streamline LCA. The first indicator here is the safety hazard, especially of the reagents employed during the synthesis of the different materials. And here we look at their intrinsic hazard profile. More specifically, we consider aspects such as the health, the flammability and instability ratings of the rings and precursors, which are based on available safety information on the NFPA, which is the National Fire Protection Association. The idea here is that a material receives a worse score if its production relies on more hazardous substances, especially when these substances are used in relevant quantities. The second indicator is the critical raw material content or criticality. For this, in this case, we screen the raw materials that are used in the synthesis and check whether they are included in the EU list of critical or strategic raw materials. The score reflects the dependence of each material option on critical input, so it captures not just the material composition, but also potential supply risk concerns. The third indicator is the cost. This is estimated from the amounts of the different raw materials and reagents required in the synthesis route, and the corresponding market or supplier-based prices. Since many of these chemicals are specialty chemicals and not large volume commodities, the price data are adjusted to better represent the scale of quantities. So here the objective is not to provide a final industrial cost, but to identify which alternatives could create a higher economic burden at an early design stage. The fourth indicator is the LCA single score. Here, the 16 impact categories of the environmental footprint method are normalized and weighted, providing a single figure that describes which is the environmental behavior overall of the material. And this allows us to include the environmental performance in the same decision framework as safety, criticality, and cost. Finally, all the indicators are normalized on a 0 to 1 scale so that they can be compared in a consistent way. And in this scorecard, a lower value means better performance. So the objective is not just select the material with the lowest value in one category, but to identify the best overall balance and trade-offs between these different sustainability dimensions. So in short, this scorecard helps transform complex sustainability data into a clear decision support tool for material developers. So to showcase an example of the assessment that we've carried within Solve, we've decided to showcase the material family of the cathode coatings. We analyzed 3 different alternatives, which were LATP, lithium zirconate, and lithium borate. And this example is a great fit because it shows the existing trade-offs between the different environmental categories that have been defined before. So here the cathode coatings are proposed to improve the interfacial stability and reduce the side reactions at the cathode electrolyte interface, which is a critical aspect in the solid-state batteries architectures. So 3 alternatives were assessed in this regard, as mentioned, the LATP, lithium zirconate, and lithium borate. And for this comparison, the functional unit is 1 kilogram of coating material. The graph on the left shows the relative environmental impact of each option across several impact categories. So to make the comparison easier to read, the highest value in each category is normalized to 100%, So visually, we can quickly rank the environmental performance of each one of the materials. The results here are clear. We can see that LATP shows the lowest environmental profile, especially in climate change and human toxicity categories. And this makes it the preferred option from an environmental point of view. In the case of lithium zirconate, it performs better than the last alternative, which is lithium borate, but it still shows a relevant environmental footprint in categories such as climate change, human toxicity, cancer effects, and resource use of fossils. So we can name it as an intermediate option. By contrast, lithium borate shows the highest burden in most categories, in 6 out of 7 assessed, and this is mainly linked to the upstream production of its key reagents, particularly lithium hydroxide and boric acid, which are the ones associated with energy-intensive extraction and refining processes. So significant chemical inputs and emissions, and in the case of the lithium compounds, also high water use and impacts on the mineral resource depletion. For this reason, from a purely environmental perspective, the lithium borate should be deprioritized as an option in order to make the assessment forward. However, there is an important point here, and is that both materials are not fully interchangeable, and their function is highly dependent on the electrochemical configuration, the interface compatibility, and the cell level performance. Therefore, these LCA results should not be interpreted in isolation. They provide valuable sustainability guidance, but they must be combined with electrochemical validation before making a final material decision. And finally, these are the safe and sustainable by design material scorecards for the different cathode coatings. In the previous slide, we looked just at the environmental profile of the alternatives, and from that perspective, LATP appeared as the best option, while in the case of lithium borate, it showed the highest environmental burdens. However, when we move to the safe and sustainable by design scorecard, this ranking changes, and this is because the LCA single score is only one of the 4 indicators considered here. The final score also includes safety hazard, critically raw materials content and cost, and all indicators are normalized on a common scale, where lower scores indicate better performance. In this case, the lithium zirconate becomes the best overall option, and this is because it has the lowest criticality score and the lowest LCA single score, which gives it the best balance across the 4 different dimensions. In this case, LATP moves to an intermediate position. Environmentally, it performed very well in the streamlined LCA results, and it also shows the lowest cost score. Nonetheless, it is strongly penalized by its criticality score, and this is because of the presence of several materials considered critical or relevant from a supply risk perspective, such as lithium, aluminum, and phosphorus. Finally, the lithium borate clearly appears as the worst performing option. It shows the highest scores for hazard, for cost, and environmental impact, which confirms that it should be the prioritized among the assessed coating alternatives. So the main conclusion here is that LCA is extremely valuable, but it should not be the only decision criterion. In early design stages, tools like this scorecard can help the developer partners in order to compare alternatives in a more balanced way, combining this environmental performance with safety, resource criticality, and economic feasibility. And this is especially useful because there is still flexibility to adjust material choices before the final cell design is locked in. And last but not least, I wanted to give a message that has already more or less been mentioned during the presentation, and is that sustainability cannot be separated from functionality. Even if a material performs very well from an environmental or a safe and sustainable by design perspective, it must still meet the required electrochemical performance, the compatibility, the safety requirements at cell level. So in battery development, the most sustainable option is only meaningful if it also works in terms of technical. So the role of this type of assessment is not to replace the technical validation at all, but to guide a better design decision from the beginning. And that's all. Thank you very much to all of you for your attention.
Thank you very much, Alberto. Very interesting talk. Is there any question from the audience? Otherwise, I do have a question. Someone is writing in the chat. Let me no. Okay. Actually, I see a question from Mary Osorio. Thank you very much for the presentation. I found the scorecards approach very interesting. Could you please clarify the methodology used to calculate the cost score? In particular, which data sources were used for the cost assessment and which cost contributors were considered the most relevant? For example, raw material prices, energy consumption, manufacturing steps, equipment, labor, and or waste treatment.
Yes. Okay, so in this case, as I mentioned, since it is an streamlined assessment, which means that there are like several cutoffs in order to make the assessment less time consuming and difficult. In the case of the cost score, we focused on prices, looking at the main laboratory supplier, sorry, and we perform a methodology in order to upscale which could be the price of these materials in order to be bulk materials to have a more representative price of which could be in order to represent a more industrial scale implementation. And answering to the second part, we excluded the costs of the equipment at this stage, and we mainly focused on those of the raw materials specifically, and also on the energy consumption, especially on the electricity.
Thank you, Alberto. Okay. We have also thanks from the chat. I also have a question which is perhaps a little bit more general, since I'm not familiar. I have a different background. Perhaps it's more related to your very last slide on the trade-off between performance and eco design parameters. So yesterday we have seen that there are several technologies which have been proposed for developing solid-state batteries or quasi-solid-state batteries. And my feeling is that research, especially at raw TRL level, often focuses on sorry, we do have some background noise. I'm not sure if. So I was saying research at low TRL level is often focusing on performance parameters and KPIs such as the energy density, operating temperature, rate capability. I was wondering whether there is any suggestions or any parameters which can be used for selecting among these various portfolio of technologies when looking at the technology from the eco design perspective. So if there is any technology which shows some advantages by default in terms of sustainability, for example, among the various polymer-based or oxide-based sulfides.
Okay, I think that I cannot answer specifically to the question in terms of specifically in each type of chemistry we should delve into each one and see in terms of in the type of chemistry in the end, depending on the architecture or which are the main compounds, you can like make an idea a little bit on which is goes its sustainable performance, let's say. But as you mentioned, the thing that has to remain at the end, and especially at low TRL projects, this is not exactly the case of Sol, but projects with a lower TRL, is that, for example, one of the main parameters and the most typical is, for example, the case of the carbon footprint, and also like in case, for example, of companies and enterprises, it's interesting to see if according to regulations and different programs that will move for the next years, like have some kind of environmental credits that pushes and gives boost to the more sustainable options in terms of sacrificing a little bit, which is the performance of the technology. But yeah.
Thank you very much.